previous videos, I explained two theorems on properties of integrable functions, proofs of two theorems. Now, this importance of this is, these theorems is like this. To prove that any function is integrable, we use these properties. What was the first theorem? First theorem was every continuous function is integrable. In a closed interval is integrable. Second theorem was like this. If a function is not continuous in the closed interval AB, it has some finite number of points of discontinuities. Finite number of discontinuities. Then also it is integrable. Now, the third theorem is like this. Every monotonic function in a closed interval AB is integrable. Now, to prove that the function is integrable, what you have to prove? We have to prove that the corresponding oscillatory sum is less than epsilon. There exists a division D of the closed interval AB, so that the corresponding oscillatory sum is less than epsilon. Then function is by necessary and sufficient conditions, function is integrable. You have studied one important theorem, conditions of integrability. What is that? The necessary and sufficient condition for a bounded function fx to be integrable is the oscillatory sum of fx in the closed interval AB must be less than epsilon. We therefore prove that oscillatory sum is less than epsilon. For that, the detailed proof is like this. I explain the detailed proof of this. What is given? Fx is monotonic in AB. We know that every monotonic function in a closed interval AB is bounded. So the first condition is function is bounded in the interval AB. Also, monotonic, you know what is monotonic function? Monotonic means either it is monotonically increasing or monotonically decreasing. For definiteness, let us suppose that fx is monotonically increasing. Monotonically increasing means x2 greater than x1 implies f of x2 is greater than f of x1. Now, function is bounded and we have supposed that it is monotonically increasing. Now, we divide AB into a finite number of subintervals. Say by this division, D is equal to x naught, x1, xr minus 1, xr, so on xn minus 1, xn is equal to b. We divide AB into finite number of subintervals by this division. This is one such division. So that the length of each subinterval is less than epsilon by FOB minus FA plus 1. FOB minus FA plus 1. This is very important. We divide AB into finite number of subintervals so that length of each subinterval is less than epsilon by FOB minus FA plus 1. MR and MR be the bounds of fx in delta. You know what is delta? Delta means this interval. Delta means xr minus 1 xr. Therefore, f of xr is capital MR, xr minus 1 is small mr, because we have assumed that it is monotonically increasing. xr greater than xr minus 1 implies f of xr is greater than f of xr minus 1. Therefore, capital MR is f of xr, small mr is f of xr minus 1. Now, we have oscillatory sum of fx corresponding to this division is, how to define oscillatory sum? R is equal to 1 to n capital MR minus MR delta R. This is the oscillatory sum. Now, it is sigma R is equal to 1 to n. What is capital MR? F of xr minus f of xr minus 1 delta R. Now it is less than, say this is important now. What is delta R? Delta R is length of R subinterval. And we have divided AB so that length of the R subinterval is less than epsilon by FB minus FA plus 1. So delta R is less than this. So epsilon by FB minus FA plus 1 into sigma f of xr minus f of xr minus 1. Now, what is this sigma f of xr minus f of xr minus 1? It is, or I write equal to epsilon by fb minus fa plus 1, and sigma f of xr minus f of xr minus 1 is fb minus fa. Now what happened? So this omega d is less than epsilon, because fb minus fa upon fb minus fa plus 1 is less than 1, so it is less than epsilon. Why we have to take fb minus fa plus 1 here? If we take only the length of the interval is less than fb minus fa, then if fb is equal to fa, suppose the function is constant, then we cannot apply this proof for the constant function. So to make the theorem applicable to even constant function, we have taken length of each subinterval is less than fb minus fa plus 1. So that is called art of writing the proof. Now once again I explain in the proof of this important theorem it is. First of all, monotonic function means every monotonic function is integrable. Every monotonic function is bounded. Therefore fx is bounded. And for definiteness we have assumed that fx is monotonically increasing. So we have this result. Capital MR is f of xr, small mr is f of xr minus 1. Next thing is we have divided that AB into finite number of subintervals by this division D, so that the oscillation of fx in each of the subinterval is less than epsilon by fb minus fa plus 1. That is the main idea here. Then oscillatory sum omega d is defined by this. Delta R is less than epsilon by fb minus fa plus 1 into sigma f of xr minus f of xr minus 1 is fb minus fa. So oscillatory sum is less than epsilon. Therefore, by condition of integrability, fx is integrable. Hence, every monotonic function is integrable. See the last one, if oscillatory sum is less than epsilon, we can write by condition of integrability fx is integrable. This is the sufficient condition and this we have proved in the sufficient conditions. That theorem we have proved this. So in every theorem, if oscillatory sum is less than epsilon, you need not prove that function is integrable. You can directly write by condition of integrability, function is integrable. I think all of you have followed the proof of the theorem. Next theorem, fourth theorem on properties of integrable function is like this. If a function fx is not continuous in infinite number of points or at infinite number of points, but these infinite discontinuities, if these infinite discontinuities has a finite number of points of finite number of limit points, then also f is integrable. This is the fourth and last one on properties of integrable function. What is the first theorem? Every continuous function is integrable. Second theorem, if a function is not continuous at finite number of points, then also it is integrable. Third one, every monotonic function is integrable. Fourth one, if the function is not continuous at infinite number of points and this set of infinite number of discontinuities has a finite number of limit points, then also it is integrable. But see, the proof of, you try the proof of this one because it is exactly similar to the second one. If a function has only finite number of discontinuities, that is integrable. You refer proof of that. The proof of this is exactly similar. You have to practice that one. The art of writing the proof. You refer that one, and if you have any difficulties and you have not followed any points in the proof, you please ask. You can ask at any time. That is why I give the PDF form of the notes also with these videos. Now I consider one problem on this. One example. Example is like this. Show that the function f defined by f of x is 1 upon 2 raised to n when 1 upon 2 raised to n plus 1 less than x less than or equal to 1 upon 2 raised to n, where n is 0, 1, 2, 3, so on, and f of 0 is integrable in 0, 1, in the interval 0, 1. This is one example which depends on the properties of integrable functions. That one of four theorems, we can apply one of the four theorems to prove that this function is integrable. Further, while when we consider when we proceed, we consider more examples. This is to illustrate only the how to apply properties of integrable functions. So I consider only one problem here. Now, how do you prove that one? Problem is like this. Show that function f defined by fx is this and f0 is 0, integrable in 0, 1, even though it has points of discontinuities. Infinite points of discontinuities. Now let us consider how the function is defined, and then we decide which property is applicable. Here f of, I consider f of x is 0, 1, 2, 3, etc. f of 0 is 0. So I consider f of 1. fx is 1. fx is 1 when x is greater than or equal to 1 upon 2, less than or equal to 1. Correct? This is the definition of the function. N takes the value 0, 1, 2, etc. First I have taken fx is, x is, n is 0 here. When n is 0, what you get? N is 0, 1 upon 2 raised to 0 is 1. So fx is 1 when 1 upon 2 less than x less than or equal to 1. I think this is clear. Next, fx is, take n is 1, what you get? 1 upon 2 when 1 upon 2 square less than x less than or equal to 1 upon 2. And it is 1 upon 2 square. Taking n is equal to 1. N is 2. When n is 2, fx is 1 upon 2 square. X is greater than 1 upon 2 cube, less than 1 upon 2 square, and so on. It is 1 upon 2 raised to n minus 1 when x is greater than 1 upon 2 raised to n. X is greater than 1 upon 2 raised to n, less than or equal to 1 upon 2 raised to n minus 1. Correct? 2 raised to n minus 1, and continues like this. Now fx is defined like this. Now function has infinite number of discontinuities here. Infinite number of discontinuities. But it has, what are the discontinuities here? 1 upon 2, 1 upon 2 square, 1 upon 2 cube, and so on. 1 upon 2 raised to n, and so on. These are the points of discontinuities. But here, this infinite number of discontinuities, this set has only finite number of limit points, namely 0 is the only the limit point of this set. Only the limit point of this set. And one more thing is, function is monotonically increasing here. How do you say that function is increasing? Because see here, interval is like this. I consider 1 upon 2 raised to n, 1 upon 2 raised to n minus 1, 1 upon 2 raised to n, 1 upon 2 raised to n minus 1, and so on. Interval is like this. See, here it is open, here it is closed, right hand is closed, and so on. It is 1 upon 2 cube, 1 upon 2 cube, 1 upon 2 square, and 1 upon 2 square, 1 upon 2, 1 upon 2, and 1. See, these are the intervals. 1 upon 2 raised to n, 1 upon 2 raised to n minus 1, 1 upon 2 cube, 1 upon 2 square, and so on. Now, when it is increasing, values of x are increasing order, and fx is also increasing value, because 1 upon 2 raised to 1 upon, it is 1 upon 2 raised to n. Consider this interval, 1 upon 2 cube, 1 upon 2 square. It is 1 upon 2 square. In 1 upon 2 square, 1 upon 2, half it is. In 1 upon 2, 1, it is 1. It is monotonically increasing. Therefore, we conclude that fx is monotonically increasing in 0, 1. and it is monotonically increasing. See the theorem 3 on properties of continuous functions. Every monotonic function is integrable. Therefore, function is integrable. We can use either property, this property, every monotonic function is integrable, or this property. But is that even though it has infinite number of discontinuities, that set of discontinuities has a finite number of limit points. Therefore, it is integrable. Both the properties are applicable here. To conclude, why this function is integrable? Even though it has infinite number of discontinuities, it is monotonically increasing. Every monotonic function is integrable, therefore it is integrable. Or since it has only finite number of limit points, the set of infinite discontinuities has only finite number of limit points, it is integrable. So I think I complete by saying you go through the videos and notes, the hard copy of the notes and then videos, you can easily understand. If you have any difficulties, you can ask it anytime. Okay, thank you.